All right, so it's my pleasure to open the session of today. So welcome everyone to our monthly invited Lab Talk series. And 2 weeks ago, I think it was, we had the invited talk by Jan Arts. And today we have Michael Behrisch from Utrecht University as a guest. And I have the honor of introducing Michael, and then I will give the word to our speaker. So Michael is a tenured assistant professor at Utrecht University in the Netherlands. I know him for quite some while, and he's publishing high quality research in our community. And Michael did his PhD at University of Constance in Germany, or they call it Konstanz, I guess, Konstanz. And afterwards, he did a postdoc at Harvard at the Visual Computing Group of Hans-Peter Pfister, and then also the Visual Analytics Lab at Tufts. And Michael's research focuses on visualization, visual analytics, and HCI. And he also has a particular focus on multivariate graph visualization and also often multivariate time series data. And with that, I'm really looking forward to the talk by Michael, and he's going to talk about visual pattern-driven exploration of big data sets.
That was a great introduction, Mark. Thank you. So you actually did already part of my intro for myself. So I'd like to cast a wider net than just talking about graphs today, right? And talk about, general, how can we incorporate the knowledge of a user in something as sophisticated as exploring an unseen data set, right? And so quick word of who I am, right? I'm pretty happy about the people of the opportunity, of the people that I could work with in the past. Daniel Keim, for example, is definitely a founder of the idea of visual analytics, and also Hans-Peter Pfister, and Remco Chang as a professor at Tufts, right, who's also with me, has started on the greatest adventure that I could ever think of, which is, forming a startup, which is a great thing. And so you're going to hear the startup once in a while. So I'm going to zoom into different kind of levels of data a little bit in this talk. But very important is to know that I'm staying also as an assistant professor or a professor in the university. And the reason for that is all the great challenges that we can have when we're talking about data analytics in the field. So I'm not working alone here in Utrecht, right? There has been actually a great success story around these people that we have here in this team, in the visualization and graphics group. I joined the team literally as the first assistant professor here, right? And with Alex together, Alexandro Telea, we actually built this entire group together. And this is really one of the success stories of my career that we have already now, I need to count 1, 2, 3, 4, 5, 6, 7 assistant professors here in the group. And recently, new people have come in. We have still vacancies open, so the team is still growing. But these people also work with talented students together. And so you see an actually only outdated image of the people, of the 15 people that are right now in our team. And I'd like to introduce to you definitely also work that these people have done, because they are the minds and the brains of the visualization and graphics group. So who am I? So what am I interested in? So Michael Behrisch, the person, is a visual analytics person. So I'm interested in explainable AI. Here on the left, you see a sequence model, which is, the baseline of the transformers, more or less, that you all know. And here the question was, can we really zoom into the model and find out what the model is doing in order to make predictions or translations from one language to another? What are the pathways that the model is doing along the way? What are the decisions to make? Understanding of high-dimensional data, totally different topic, or kind of related topic, is Here you see this table-like visualization with the idea that we're working a lot with psychologists in the past, and they are not necessarily too much data savvy. They're data savvy, but they're not too much potentially, machine learning experts. So how much can we really hide complexity, visual analytics complexity, data analytics complexity, the entire plethora of machine learning, right, from these people, in order to still come to very, very fruitful explorations. Gonna skip the next one, pseudo, because I'm most likely you're gonna see it again. But in general, the topic of scalable pattern exploration is something that interests me. And then also in the same vein, there are other directions that are more coming naturally from the visual analytics idea, where you have steerable algorithms. So right now we're living in a world where you're applying an algorithm and you just expect that this algorithm does the thing that you want to do. But why does it need to be like that? Why can't you just steer an algorithm and say, okay, this part of the result set was actually what I was searching for, but this part, could you recalculate? Is that something that you could do again for me in order to see whether there's more in there? And this brings us immediately then into the problem. What if these algorithms are bringing more and more what I call visual patterns back? How do we explore them? How do we explore them in context, right? How do we navigate these complex visual spaces? And also related to that is, how do I communicate as a user actually to an algorithm or to a computer what I want to see? Right? I'm starting an exploration, and the hardest thing is, how do you start an exploration of an unseen data set? How do you know if when you found something, what you should look at next? And how do you know that you're done by exploring a data set, right? And this is this learning and steering of the user interest, communicating your user interest to the computer is one of the other things that I'm very interested in. And so all of this on a higher level circles back to this user-centric exploration of large visual pattern spaces. And there's this triangle over here where you say, okay, data analysis or visual data analysis is solved at the triangle between visualization, data analysis, and interacting with the data. So let the computer number crunch as much as possible, but let the user understand the steps in between and steer the algorithm with the common knowledge, with the domain knowledge in the right direction, and let us use visualizations in order to be able to understand the exploration process in between. So in this triangle, I'm definitely found on the visual data science and information retrieval side. I'm very interested in cognitive psychology, cognitive aspects, biases, right? And also perception. And I'm certainly not a person who's doing a lot of graphics and scientific visualization, but I can be literally found, as you've seen it already before, in the InfoVis domain. So the way this works in this entire presentation is I have got some chapters in here, and all of them are starting with a potentially, starting publication, right, that you can look at or just skip over it, right? So first of all, what is visual pattern exploration? Why am I interested in that? So let's start really easy, okay? I'm going to give you these three scatter plots, and now I ask you, which of these scatter plots is actually interesting for you? Then naturally, most of the people in the room would say, okay, the first one, certainly not. This is way too cluttered, cannot make heads and tails of it. The second one is interesting, but it actually, doesn't reflect what I want to see. But the right one, that's where I see groupings in the data evolve, right? And so here you see directly that this question itself was ill-posed. Why is the second scatter plot not of interest for you? Because it does not resonate with your task that you want to accomplish right now with the data set. And if I would have told you that the task that you want to accomplish, you would have is a grouping task, you would have certainly said, okay, the right one is definitely the go-to solution, right? So what we find out is that this discrepancy between the pattern space or the conceptual space of what the visualization is showing, that needs to necessarily match your user task at hand currently. But let's take the same example and modify it a little bit. So you would have all said, okay, the black dots were definitely meaningless. But by just adding another, what we're calling visual attribute on top of the nodes, here the color, and split it up into high, medium, and low, you would say that is the pretty effective visualization, correct? And so we can also say that the visualization parameters need to definitely reflect the dataset characteristic to make a visualization actually a meaningful one. And there's actually one more step in here, which is this one. Let's take that image back. And now I give you additional information that this is actually a logarithmic scale. So there will be a few people in the room, not many actually, we found that out through research, that can extrapolate that the linear axis dimension over here will distort the entire visual pattern that you see on the logarithmic scale. So you're going to see this spread out, this clumping on the bottom left, but then this spread out axis on towards the top right. So we can say that the visualization parameter directly influence the user understandability and even which kind of users these kind of visualizations can be useful. So coming back to this triangle, right, of task, data, and user, then you can say, okay, you're starting with a visualization somewhere over here, and you have this performance valley, right? On the bottom left, it's red, not too good, right? On the user side, it's there. But what if you can literally improve your visual encodings, the part of the data that you're showing to the user that is more and more of interest, and the visual attributes in order to accomplish a task even better? And that is something that we formalized at some point in the quality metrics for information visualization, where we see here we have this inner part. I don't know whether you can see actually my mouse pointer. Can you give me a thumbs up if you can see my mouse pointer?
Yeah, we can see that.
Cool. Yeah, so you have this phi over here, which stands for, okay, these are the parameter settings, how you came up with this visualization. So parameter setting can be, for example, a scatter plot is made out of x's, right? One axis in the y direction, one in the x direction, right? And in there you have a logarithmic scale or a linear scale, something like this. And that naturally has to adapt to the data at hand, the user capabilities, and the task at hand. And if you're measuring that with one number, right, that says one dot over here, right, that would be a quality metric, okay? Now, if you're trying to optimize this quality metric in here, or this quality criterion in here, right, then you are going for a quality metric. So what can I modify in my scatter plot right now in order to make it more useful for you as a human in your partitioning task? Typical high dimensional data analysis problem. You have way too many dimensions, right? Which of them do you really show to the user to show correlation, for example, right? And this entire thing, this thought concept is actually also not too much new, but what I'm bringing into this twist is we have this mid-level perceptual task. And in the old days, this entire field was driven around, let us just remove the clutter from a data set with 1 million scatter plots. If I'm just screening the ones out that are cluttered, right, I'm going to be left with the ones that are potentially interesting, right? And the next approach for that, that's what I'm advocating, is a pattern-driven analysis that's saying, if I can ask the user, what kind of task do you have? I can write a feature descriptor that will only show me the patterns that I'm going to need for my current data analysis task. And this shifts away from cognitive overload to analysis focus. And this is what the visual pattern analysis is approaching. Just for the sake of completeness, let's zoom also into the other levels. So on the low level, you have things on color research, Gramazio, Mittelstädt, all these people that have done amazing stuff around color research and how to use effective colors for your visualization, because color is an important attribute in visualization design. Then if you ever have time, 39 studies about human perception in 30 minutes. It's definitely an outstanding blog post. So look into this if you want to know more about how users perceive data visualizations. And then there's also high level. And this is really cool because there are things around, if I show you a visualization, how likely is it actually that you can remember this? And if the central goal of visualization design is to convey information over time, then this is certainly something that we need to take into consideration. Visualization that you're going to remember for a long time, right, is something that is more prone to data storytelling, for example, than anything else. And there you have also the field of aesthetics. Nice. So let's zoom into stuff that we have done in the past, also by my totally gifted PhD students in my group. And let's talk about something that is interesting me, right? High-dimensional data projection. And here we were so super lucky to actually win the Best Paper Award at Eurovis last year on this work. That's not 2023. It's 2023 and not 2030. Yeah. So the question was actually, do actually all patterns in projection mean something, or is that just an artifact? And so, quick recap for the people in the room. Many of you know that already. Let's say you have a big table, okay? And the data space here, or the complexity comes not from, as Jan Arts would literally describe it, right? I'm taking that partially from him. The complexity here comes not necessarily from many rows in there, but the complexity comes from not the abundance of data, but really the complexity of the data. So we have many of these columns, many of the dimensions, right? And if I ever wanted to see that in a logical manner, I would have to project down from an Rn space to an Rq space, where Q is significantly smaller than N, right? So we say that, let us give me the best dimensions. Give me the best dimensions that are potentially of interest for analyzing this data set. And here you see that clustered plot where we are projecting into 2 dimensions. That's why we can plot that on the X and Y axis. And here you see, for example, there are multiple algorithms for that. One of them is UMAP. There are many others. Okay, so interesting enough, we asked the question, if that is a lossy transformation from Rn to Rq, does that naturally mean that we also can trust all the patterns that we're seeing here, right? Because on the perceptual side, here you see the same data set with TSNE projected and one with UMAP projected. They are looking similar, but not actually the same. Right? So, for example, you have this elongated cluster over here in the middle. Here, this is totally cramped together. This cluster is very widespread out. Here, it's very narrow to each other, right? So, interesting enough, I did with you the experiment on how to analyze this projection plot, right? But the way I did this, I explained it actually in visual patterns. You see clusters, you see straighted aspects, you see elongated data groupings, and so on and so forth. So what that naturally means is that a pattern naturally comes out of the data, sure, right? This is what the data should be, reflecting on the 2D screen. But the algorithm is contributing quite a bit in terms of how it's representing these data attributes to you. So, and if you ever worked on projection work, you would say that you can look at a projection and say, oh, this is UMAP, certainly, right? Or, oh, this is PCA. And so we actually did a little bit more research into what that means. And the question now becomes, when you have all of these projection options, which of them is actually more correct? Is the left one more correct than the right one? Or is this entirely an artifact of the things that you're producing due to how you designed the algorithm? Might be a little bit complex, right? But let's go a little bit further on that and play that thought concept a little bit further, right? So we say that the visual signature is the thing that you're interpreting, but it's not controllable. And with Sharp, we actually put an algorithm out where you can directly control the shape of the visualization that you see. So how do we do that? For many people that will look at this will say immediately, okay, this is an autoencoder, right? And we are basing our work on the great stuff of Espadotto in 2021 on self-supervised dimensionality reduction. The question here is, can we learn dimensionality reduction from an autoencoder, right? And so this is no magic. What comes out, this is how it will look like. This is a typical scenario what SS&P will produce. You have the high-dimensional data. You're piping that through an autoencoder. You retain for every of these points a 2D coordinate. You're just plotting that onto the screen, right? This is an autoencoder plus what you see here, separating component, a cluster separating component, so that you can keep these clusters apart. And the way this is typically done is by clustering in between and giving these points pseudo labels. So what comes out of it? What is the visual signature of this algorithm? Well, the clusters are elongated. You are wasting some white space, and these groups are collapsing, right? Now, if these are all parameters that you don't want to see, what could we do against it? What could we do to make that more effective? And this is what we're doing with Sharp, where we are using this autoencoder over here, and we're not using now an Cartesian space, but we're sampling from a distribution. And you might also say, okay, cool, this is nothing new for me. I've seen that before. That is actually what's called an autoencoder, right? The interesting thing over here is if you're sampling from a distribution and you are restricting the distribution space a little bit with the hyperparameter P, oh, sorry, that was a bit fast, then you have literally what is called in the machine learning world a regularizer. What this does is, first of all, by sampling from a distribution, we can have not anymore point-to-point allocations, but point-to-region allocations. Right? This gives us a lot of flexibility of what we want to do. And then we have this shape regularization aspect, the P over here, that is actually there for preventing, you know, this wild animal to explore the environment, right? So this prevents us from learning too wild distributions over here. And this is what we were showing under the term of shape regularization. And what you can see over here is, for example, this. We can mimic with Sharp actually approaches like UMAP or PCA by just taking a different distribution function on which we're sampling over here. This is what you see in the middle, right? And we're just restricting that space. And now think about it, right? You're taking a normal or a Gaussian curve, right? In 3D over here, that's what you see on the left. And you're sampling from that. What naturally will come out is that your spread of the input data will be rounded. And this is a typical artifact that we've seen from UMAP. That's a typical artifact that we've seen, for example, also from PCA, right? But let's get a little bit more wild over here, right? If these are all parameters, why don't we just play around with this and see where we can get? So here we are doing a normal distribution and a little bit of a shape parameter on top. So we can now get squared projections where every of these clusters is now squared. Why should I care? Why should I do this? If my tool is entirely set up to do data selection tasks with a rectangle selection, this might be the projection that you might favor, right? Because it's easier to select the points in this projection plot, right? While still maintaining the idea that points in the projection space need to be close to each other if when they have been in the high dimensional space, they're close to each other. But we can even do more. We can do triangle shapes by sampling from a Dirichlet distribution and just apply rotation, translation, scaling, use barycenter as coordinates, then you're ending up with something like this. We can even go further, but we stopped our work actually here because each shape requires a specific sampling scheme, and this can be really mathy at some point in time. But the general gist of it is we have a projection technique that can form convex shapes to your liking, whatever you want. If you wanted your visualization to look like a smiley, doable, right? And still obey high dimensional data analysis approaches. So I'm not going to bore you a lot with evaluation, but just for the sake of it, I'm going to show you something on here. right? We evaluated this on multiple data sets, multiple approaches, multiple parameter settings. But there's one actually that is very interesting, right? When you recall, there were these 3 components in here. The shape regularization was just one. And the question is, how strong do you give this beta component to the algorithm? Because if you just make it 0, you ignore it, you are ending up with with SS and P, which can be seen also as stuff that, axis aligned projections would do naturally. Then you have something like a sweet spot around 0.1 of the strength that how much you want to shape stuff. My slides are advancing all the time, sorry for that. And then you're coming to this spot where actually the impact of shaping gets so big that the algorithm is not actually projecting anymore, but just tries to satisfy roundedness over here. And that's what you would say is definitely a very bad projection plot. And you can see that also from all the standard quality metrics over here. At some point in here, 0.1 is typically the case, where all of these quality metrics are deteriorating a lot, right, over all the different data sets. So that is also to say, use it with care. This is not just a nice to have approach where you don't have to think about it, but parameter sensitivity in all of these projections are given. What's cool about this? Why am I excited? Other than you can make arbitrary shapes. We were 50 to 80% faster than TSNE and UMAP, right? And now the things that are really interesting me is this scales linearly in the amount of samples. So no matter how big your data set is, you're going to get a very fast projection. And you can even start training on a subset of your data set, right? And then train later, continue the training later on. But you can already use this encoder approach, right, to project it downwards. And this is really a powerful idea, that you can have an algorithm that starts already calculating for you, right? And then you're coming back to it, right? Once the quality of that is good enough, but for now you can see where this is actually going. Cool. 26 minutes. I'm gonna zoom over this here as well. A very interesting work on multivariate time series exploration. So context over here, I'm working with a company called IAV in Germany. They have these prototype of cars. And it's very, very interesting to see they are literally running around with a cluster of sensory within these prototype cars that they are running against every possible scenario of how you can ever use a car. And so what comes out is a time series, and actually not just one time series, but you're coming up with a multitude of time series of sensor data over time. So the problem here is these data analysts have super high dimensional data, right? A lot of time series over time and a lot of sensors. They have only very meager labels, as in, instances when something really was not correct in the car. And this is something that they would like to find again in a root cause analysis. They have an infinite time pressure. So everything that they're doing needs to be fast. And then they have this problem that sometimes they disagree. So they cannot even train a classifier and say, okay, is that an interesting pattern? Yes, no, maybe. Right? Because they are running very often into for me, this is interesting because I have seen this aspect of it. For other ones, it's not, right? So the research question is here, how can we assist these users in spontaneous pattern search in these multivariate time series with respect to subjective efficiency? So we're not the first one that had actually this problem. So multivariate time series is not new. Relevance feedback was also not new, something that we're introducing here in this work, in this piece that we did. So there has been stuff that I have done together with Yun Song, our PhD students on that, in order to do SAX-like description of multivariate time series. We have locality sensitive approaches that have been done for retrieval of multivariate time series in the past, but they were clunky and not usable too much. There has been stuff on telling the user, telling the algorithm on how to get better in your exploration path from Eamon Koff. And we have this best paper at Eurovis 2020, I think, which is called Peaks of, well, many people that Mark definitely knows on the authorship list, where this was all about analyzing biomedical data, right? And here the approach was to have a deep learning and autoencoder-based approach, again, for the retrieval and analysis of the respective patterns that, you know, the biology domain is searching for. And we are shifting that to a now different domain with a slightly different approach. And what we are trying to do within this paper is the relevance feedback, multivariate, locality-sensitive hashing-based retrieval. That's a mouthful. So what does that mean? So if you're new to this, I think that many people will not have heard locality-sensitive hashing before. General hashing is something that pops up in every computer science curriculum, right? The idea is I give you a file, I'm going to hash it down, and even if in that file has one bit changed, the hash needs to be different, right? And I'm doing that for duplicate detection, encryption, et cetera, et cetera. So that is called general hashing. Now, if I'm inverting that, then I'm in the hashing universe of locality-sensitive hashing, where I say, I take that file, only one bit has changed, then hopefully the buckets in which they are ending should be almost the same or should be the same. And that would mean I cannot guarantee you mathematically that these two files are the same, but I definitely know that they are near duplicates, right? And this is literally one of the things that you're using when you're doing Spotify search or you're humming into your Shazam or something like that, because you're not necessarily searching for the absolute appropriate match, but you're searching for a near duplicate to your humming, right? And this is what's called locality-sensitive hashing. So what's the concept of this? It's actually totally stupid. You're taking these points over here in a plane. And what you're doing now is you're just randomly laying hyperplanes in there. So there's this magenta line, the blue line, and the red line, right? And now you just say, okay, everything that's above is a 0, and after that, below that is a 1. So when you look at this, right, the point A over here is above the red line, is above the blue line, and above the yellow line over here. That's why it ends up in this bucket. B the same, right? Let's take C over here. You have actually C is above the 0, the red line. It is below the yellow line, and it's above the blue line over here. But you can see immediately a problem over here. Okay, I cannot even really well describe, you know, these spaces that I just accidentally have missed, right? And this is why you're doing this same process just several times. And mathematically, it has been proven that if you do that a few times, and it's actually surprising how little of these hash tables you're going to need, hashing functions you're going to need is around, you know, depending on the dimensionality of your input data, but it's going to be 5 to 10, right? You're ending up with these 5 to 10 hash tables, and you could do perfect, almost perfect near duplicate detection. So why don't we use that if that's so super powerful? And it literally involves the most sophisticated data analysis approach that you can do, which is guessing, right? So as fast as can be. Why can't we use that for our data analysis problems? So you would do something like you get your data in, you train a model. It can be bad in the beginning. You take some representatives out of this, and then you ask the user for relevance feedback, whether this was good. If it was good, the model was good, you just say, okay, the model should stay like that, or you just optimize the ones that didn't fit. And this is literally what we did in this work with Pseudo on multivariate time series exploration. So you have these time series, right? 3 of them over here. And what we're doing is we have a window-based approach. So you have a window that you're sliding over that, right? And then you're projecting that more or less with this hashing algorithm in this hash space, okay? And what you're doing on top, you're doing the same with a query. So now you can ask, okay, what is in the bucket green around that query? Nothing. What's in the bucket slightly less green in that bucket? Well, they have two near duplicates, near neighbors, right? So this is great because the operation for retrieval is almost for free, because it's just checking a few hash codes or binary codes against each other, right? So in itself, you're working only with these hash tables that from which you can always say, these hash tables are nothing more than just buckets. Let's look into each of the buckets, just pull a few of these labels out and ask the user, is this actually subjectively something that you think is cool for your current analysis task? Then give it a thumbs up or give it a thumbs down, right? This is what we're doing over here. And that is the relevance feedback that we're letting flow back. And this is the contribution of this work here into the adaptive hash space. In the interest of time, I'm going to skip all of this. But the quintessential aspect of this is we have a way to measure, okay, what is really the impact of each of these hashing functions on the retrieval process. And we would just like to promote the ones with a weighting factor that actually are reflecting what you want to see currently. Okay, so let's see that for a second in action over here. You're zooming into the data set. Over here, you are setting a query. We have now over 300 megabytes of calculations going on. And in under 15 seconds, you have seen already a result coming up. You're learning a distribution from that. You can see, okay, these results are good, but over there, you know, towards the uncertainty, the right uncertainty, it's getting worse. We want to exclude that from our analysis, or here we want to say, okay, these are really good results. Please stay in that exploration direction. These are the ones that I definitely don't want to see, and so on and so forth. I can do that on instances or on entire tables. And then I can train the algorithm again, and I can refine my exploration over and over again. And you see the second step gets even faster in terms of the found patterns and how fast this is all operating. Skipping over the experiment section, what I wanted to actually point out over here, this approach is highly scalable in the number of tracks, and this is very important because our cars are running around with hundreds of tracks, and you see that it's almost scaling constantly in the number of tracks in terms of calculation time and how much effort we are having to do that to calculate. In terms of relevance feedback, the typical reviewer would say, okay, but how much relevance feedback do I need to give in order to make that even better? We found out that only 3 to 5 feedback rounds are typically enough to boost performance significantly in the exploration field. And this is something, you know, that is for me a great breakthrough, because we are going into the active learning direction of how to improve things. I am rushing a lot, and I don't know, I've got 45 minutes, Mark, right? Cool. So here's the thing that definitely Mark has been waiting for. This is, I told you I was born out of Constance, where I was working from day one on graph data analytics. And graph data analytics is great stuff because, you know, not only social networks are based on graphs, but right now with this advance of, you know, better technologies such as graph databases, we're getting to something like biology knowledge graphs that are helping us to cure Alzheimer's diseases. We have all the AI assistants that are working with some form of, when they are good AI assistant, they're working with forms of knowledge graphs to check whether this really makes sense, what they are proposing out of latent space, for example, if they are transformer-based models. The entire fraud detection direction is working on this. If we want to have something like circular supply chains where we are working with sustainability topics, then we cannot work without graphs anymore, right? And so this is what is interesting me, but there's a slight problem, right? So typically people say knowledge graphs are the easiest thing in the world. You just take your data, you just add a few relations to it, right? And you're doing that with a little bit more and add a little bit more relations and a little bit more semantics. And then you're ending up with this knowledge graph, right? The deep dynamic context, right? But what this actually looks like in reality is this, right? So the left side is literally a small query of something in the knowledge graph. So you have analysis code that nobody understands. And then even if you get some data out of it, you're running into these useless visuals that are called a hairball for a reason, right? Where you cannot actually make any logical analysis out of this. So reality is big frustration over here. So, and this is literally something that let me and Remco actually start, Graph Polaris, where we say, okay, from the business side, there are business owners that have to hire expensive experts for maintaining the use cases, but you say immediately, I don't care about expensive expert and I don't care about business owners. Well, it's the same for researchers, right? Researchers they have to spend a lot of time for developing their data analysis scenarios. And this is especially true in the biology domain. And this is very often disconnected from business decisions because we have this accessibility gap towards the graph. And here the same applies for the research domain. And also the entire process is right now too slow in order to get into a meaningful exploration dialogue. So what we are doing, and I have to apologize right away, these are as outdated images from Graph Polaris that there can be. But what we have designed is actually Tableau for graph data analytics, or we are in the process of doing this. So what Tableau, Graph Polaris is all about, it's a no-code visual analytics tool for exploring relational databases. We are supporting an end-to-end process. What that means, I'm going to come to in a little bit. And we have actually incorporated a lot more visualizations than just the standard node link diagram in our tool. And this stems from my intrinsic motivation of why I started this entire approach, because I say that a lot of the great work that we're doing in research has never made it actually to a commercial world where we can really make an impact with these kind of visualizations that we are just producing for a paper. So why don't we take this and bring it out to the world in order to make a real impact? And this is what I call explainable explorations. So let's skim over that. What you see on the left here is what we're calling a graph schema. This is not necessarily the graph data, right? This is how you modeled your graph schema. And on that bottom over here, you see that with a few drag and drop mechanisms, right? Easy to understand for everybody. You can add some filters over here. And what we are doing in the back end, transparent for you, is to write this complex code. Here you see AQL that we're sending to the graph database. It comes back and we're not showing you the data, but we're showing you a visualization thereof. Okay, so this is one of the core functionalities of Graph Polaris. So why this gets me actually excited is the research potential behind this, right? So on the left side, the graph schema, this is as complex as can be because these graph schemas are very early becoming very, very complex. So multi-scale graph visualizations is something that is a very, very hot topic for me in the future. Augmenting the graph model automatically. So can we take a graph schema and say, why don't you merge these two schemas together? You're going to have something that is much more complex and much more powerful to explore. On the query definition side, the interesting thing is what we built actually is a so-called visual graph query language. And this is as powerful as can be because you could stand with your data science department in front of a whiteboard and use the same visual language in order to communicate with each other, right? And that is something that is missing a lot. The accessibility of these databases is not necessarily because the people are just too stupid, but it's such an immense effort to tell, I have found this fraud. It contains all of these aspects. Can you check whether you find that in a different context again, right? This is something where a lot of information gets lost. And so having something like a visual query language is great for these people to have. So here on recommendation engine is the next topic that I'd like to zoom in. What happens if you're dragging a query into this? What we can do is we can do post analysis. We can say, hey, listen, rather use this visualization. This is what Tableau knows as the show me button, but we can go way further, right? We can say, we found out that there's categorical data in your data set. We are splitting up your task into these distinct ones. So here, visualization guidance, ML guidance are interesting research potentials. So, and for sure, on the graph representation side, this is very clear. There are much more visualizations. Here you see one that is out of the 80s. It's called semantic substrates. That is uber powerful for dedicated analysis tasks. And here I'm closing the loop to the beginning of my talk. You need to know what the analysis task is in order to recommend the right visualization for the user. But the data can give you clues of what you could do. So for example, if you have a data set that comes back that contains geodata, why not show it on a map? Because I can assume at least that the user wanted to see it on a map, right? These are the logics that we are applying in Graph Polaris, right? And there's more to come on the visualization side. Cool. Let's wrap up with the research agenda. So hopefully I've convinced you with some take-home messages, which is the pattern is the thing, is the instance that you're actually up for in the exploration, and pattern-driven analysis is definitely a powerful tool. It can only be used if it's wisely adapted in visual exploration interfaces without interrupting actually your workflow. And the way to use that, my research way of doing that, is through what is called a visual quality metrics that are screening mechanisms for the data, whether it contains this respective data set. This respective visual pattern. And here, again, I need to shout it out, right? Visual analytics is a key enabler. Not having this stringent process anymore of, I train an algorithm, I apply it, and then I let it go, and I don't let it look at it anymore in the future. This is an old school approach. You need to have visualizations at least for end results and also for intermediate results. And now if you have both of them, why don't you make the entire exploration process a steerable process where you can adapt what the algorithm should produce? Cool. I rushed through, stopping with a thank you slide of the collaborators that I had in the past. And a special thanks definitely goes to my bachelor and master students. I've got plenty of them that are doing insanely good work for me. And with that, I'm open for questions and say thank you to all of you.
Thanks a lot, Michael. Very exciting talk. I see that you burned for the topic. I liked it. And I will remember your mimicry reviewer voice when I read my reviews next time. So we have time for a few questions. That's great. And I see also some externals here. So everyone here on the call, please feel free to ask questions. Just unmute yourself.
Yeah, so I have a question. Thank you for the great talk. It was really interesting and very relevant topic, especially at the end. So for the last tool that you showed, maybe I missed it, so I'm sorry, but I wanted to know whether this is like a standalone tool or whether it is feasible to include this in, for instance, a larger visualization tool in like a React framework, for instance, something like that.
So fun enough, Graph Polaris is all open source, right? And all the components, I say components, right? Because I'm thinking React. All the visualization components are literally open source and freely available for you to use if you want it, right? It's git.science.uu/Graph Polaris. So feel free to check it out. So what this is a fully web-based interface. The backend is a little bit beefy, does not really fly all the time for all the users. We're working on that. It's a microservice-based architecture in the backend. But anyways, you were asking about the front end. Yes, sure, use it, please.
Okay, great. Thank you.
That's also one of the things that I need to add to that, to generalize that. The way I envision actually Graph Polaris is that this is an amplifying mechanism that says, okay, this is stuff that the visualization domain has done in the past, right? And we are showing that off just to a wider audience, but we're not taking, the credits for it, because this is literally what I define as standing on the shoulders of giants, right? They have been insanely powerful and brainful people, wise people that have come up with many of these visualizations. And crediting here Ben Snyderman, just because we saw semantic substrate, or PowerVis, Jean-Daniel Fiquet. We have no tricks in there very soon. Nathalie Behrisch, right? These are all the people that have done the crazy work that can, bring business value to the people. Happy to get more questions.
I'm having a question. Like you showed the projection in the first task. I wanted to ask that you somehow assume that you know the distribution of your underlying clusters in the data. Is that correct, or did I miss that?
No, we don't. We are applying a clustering in order to find it out.
Okay.
So what comes in is literally all black points, right? But in order to have a cluster separation component, let me jump. I hate the slide jumping. That's why. Here. Right. So what we have is we have all black points, right? But we have this cluster separation component over here. And this comes literally from running one time a clustering component over the input data and say, okay, auto. That's where literally these cluster labels are coming.
Thank you.
And that's a hack, right? I mean, if they are there, you don't need them, right? Because then you can skip that step. But in the typical scenario, it would be nice if all my high dimensional points were already clustered for me nicely into my buckets that I want to explore, right? Because this is literally where the semantics comes in. But at least data-driven, I can do it, right?
I have another question about Sharp. I'm Andreas, so thanks for the very interesting talk. I'm a postdoc in Mark's group, by the way. So I also have a question about Sharp, especially at the end when you mentioned the out-of-sample extension capabilities, so applying those pre-trained embeddings to new points. And in my experience, especially when working with parametric extensions of TSNE or UMAP, what usually happens when you add a new point is that it's placed very close to whatever happens to be the closest point in your training data set. And the use of white space is not really intuitive. Well, it kind of makes sense because there's no information at all in those places of the embeddings. So I was wondering if adding those shape constraints that you do here in Sharp and expanding the clusters artificially, if that somehow changes the behavior in your experience of the out-of-sample extension.
So, very great question, Andreas. Great that you asked it, right? So one of the things that I need to mention for Sharp is this is where experimental design really hits mathematics, right? So really proving what I say, I would take that definitely with a grain of salt. I can tell you what we found out in our experiments, right? So we found out that typical scenario, right? You're training with a very small data set, right? A very small sample. And then you're just looking at how does one cluster evolve, right? And then what you naturally see, yes, you see these growing clusters, right? Clusters are growing outside. So depending on the restriction or this shape restriction, you see that the entire shape is scaling, right? Which is actually a nice aspect because this is something that I as a user can understand, right? So this is nice because it does not go too far away from the centroid. The centroid, my interpolated centroid, will be always in the middle of the shape, right? This is a perceptual problem, right? This is not a mathematical or data analysis problem, right? And so this is something that we saw. So the shapes rather grow, right? And then you can do artificial experiments where you after that only let the projector see one class, right? And see how the other ones are forming. At some point, you noticed that the topology of that one cluster is overshadowing the others. And the other ones are deforming into a blob, right? A very small blob. And the other one is still trying to grow exponentially in terms of, or not scaling in terms of the size, right? But I would not ever know how to start explaining that in mathematical terms.
Thanks.
Michael, may I continue with the question? So,
Absolutely.
or actually two questions. So the first question is, I mean, this relevance feedback is really powerful. And now maybe that question also resonates with all the AI students here on the call. If you now think about LLMs, right? And you have this kind of conversation with a large language model that has access to more specialized trained models for specific tasks, this long chain approach. Do you think there is potential for this pattern-driven analysis? Where do you like, if you do a prediction of what will be possible in at least 1 year, what would you say?
I was invited 2 months ago in Eindhoven, where Fernando Pavlovic, the person who did the projection explorer, was sitting in the audience, right? A good friend of mine. He actually asked absolutely the same question, right? So here's my 2 cents on that, right? LLMs, or in general, large language models will revolutionize the way we work. We'll stop. I think we're going to get in tedious tasks much faster, right? The interesting thing is, if you're still, I do not trust anything that comes out of ChatGPT, not on the content trust level, but just not that there are artificial grammar typos in there, something like this, right? Or something that just doesn't make sense. So I'm still the person who's analyzing the intermediate step, right? For me to get to the end report, right? And this is something that I think is that's a human and visualization problem, right? And I think that also in the future, we can certainly we can certainly have domains where we can train large language models that will do an outstanding job. We don't have to prove them. We don't have to double check them, etc. We've seen these great demos very recently of ChatGPT GPT 4.0, right? Where these two mobile phones are talking with each other, right? Have you seen that demo? So this is absolutely great stuff, and I think in not mission critical domains, this is absolutely no problem, right? And there we're seeing that definitely that our world will revolutionize. But whenever you need to be sure that you're on the right track, you're gonna have to have a way to explore what the model has actually at least thought at this instant in time.
Yeah, I agree, but that also potential for visualization to like contextualize the results, right?
Absolutely, absolutely. So, Mark, you know that I'm not the arrogant person in the room, but I sometimes shake my head because the visualization domain has done since 20 years what's called model visualization, right? Now just the models have changed. Right? We have done things on explaining what a regressor actually does. We have done stuff on linear models, decision trees, etc. Just our models get more complex. But the approaches around that are not necessarily conceptually very new, right? We are actually doing post-hoc analysis or parameter space analysis. Don't quote me on that, right? There's definitely cool stuff around there. But we have thought about this problem already. And I think there's much more to be done in order to come to the level where we can really trust, taking that word a little bit lightly, right? Where we can trust an AI algorithm fully.
Yeah. Thank you very much again. So in the interest of time, I think I have to close the session now, and I'm sparing the question of what is the closed part of graph Polaris, what does it contain? But we can take that offline. All right, yeah, thanks again so much. It was super interesting, and my last duty is now to announce our next speaker. The next invited talk is on the 19th of June, given by Robert Krüger, who is going to visit us. I think Michael also knows him. He's now like newly appointed assistant professor at NYU in New York, and he's going to talk about scalable visualization and his work on spatial multivariate data analysis. And yeah, with that, I'm closing the session. Michael, thanks so much for taking the time, and hope to see you soon. Bye-bye.
Yes,
Thanks, everyone.
Thank you. Bye.